Okay, now I will start with the theory first. So as we know, the topic 3 is about the bending of beam, or we can call the bending as a deflection, which defined as the degree to which a structure can be shifted by a significant amount of load. And then the beam is a long portion of a body capable of supporting any load on a resisting bending. So as we combine this together, we can get the beam deflection is the when the force is applied to the beam, we can get the deflection of a beam in a certain direction. Usually we will use the millimeters as a unit for the beam. There are numerous formula that we can get from the cantilever beam. As you can see on the table here, we have 5 types of cantilever beam, and each of the types have different formula to it. Next, as we know, every situation have a cause to it to happen. So in this slide, I will discuss about the factors that can cause the deflection of beam. So what is the factors? The first one is the beam materials, or the elastic modulus. The second one is the beam section. We can get it from the moment of inertia or the self weight of the beam. The third one is the loading on beam, either the dead or live load. What is dead load? Dead load is the permanent load, like the weight that acted on the beam. And live load is a load that can sometimes that can be removed or can be decreased or increased the load. Next is the span of beam. We can know the span of beam, how long the beam will stay there. And then the last one is the beam support type, like a fixed support or hinge support.
Assalamualaikum, my name is Ariana Tasha binti Zuraidi, metric numbers DD190253 from Group 1, Solid Lab. I'm going to present my part from experimentary, bending of beam, which is observation. We learned from the 3 experiment that we conduct that we will need to use the gauge meter for all the 3 experiment. The information gathered will be utilized to calculate the Young modulus of the beam later on, which will help us to better understand deflection. The weight of the load is varied in the first experiment to investigate the relationship between load and deflection. The data from 3 experiments has been documented in the table. The deflection of a beam is directly proportional to the load as illustrated. As can be seen in table 6.1, the relationship between load and deflection of beam is exactly proportional. As the load increases, the deflection of the beam decreases. The deflection of the beam is 0.288 mm at a 5 Newton starting load. Then with a load of 10 Newton, the beam deflection increases to 0.54 mm. Following that, the deflection of the beam increases to 0.88 mm and 1.15 mm for load of 15 Newton and 20 Newton respectively. The relationship between span length and deflection is strictly proportional, as seen in table 6.2. The data obtained shows that as span length increases, the deflection increases in lockstep. The deflection can be enhanced by increasing the distance between each barrier, according to the experiment. The experiment starts with the shortest span length of 300 mm, which result in 0.07 mm deflection rate. It continued to rise to 0.23 mm and 0.35 mm for span length of 400 mm and 500 mm respectively. With a rate of 0.52 mm, the highest deflection value was obtained at 300 mm. Finally, in the third experiment, table 6.3 shows that as the height of the specimen is reduced, the deflection rate decreases. In the experiment, 3 different specimens with the same material but different height were employed. When we utilize different specimen dimension, we can observe that the result change depending on the specimen height. The deflection rate fall from 0.46 mm to 0.15 mm when the specimen height is increased from 4 mm to 6 mm. It continued to fall from 3, reaching a height of 0.08 0.08mm when the height reached 8mm. That's all from me. Thank you.
Assalamualaikum and hi, my name is Ahmad Livia Manduddin. My metric number 819088. So I'm going to talk about calculation for experiment 3, which is bending of beam. Based on the data observed at experiment 6.3, calculate the Young modulus of each assessment. Formula is beam deflect equal to weight multiplied by length power of 3 divided by 48 multiplied by Young modulus and multiplied by moment of inertia. Another formula is second moment of inertia is equal to weight multiplied by height power of 3 divided by 12. In first specimen, search for the moment of inertia, which is equal to 25 multiplied by 4 power of 3 divided by 12. So you get 0.13310 negative 9 meter power 4. And Young modulus we get 0.46 multiplied by 10 power of negative 3 equal to 5 multiplied by 0.5 power of 3 divided by 48 E multiplied by 0.13310 multiplied by 10 power of 9. So we can get Young modulus is 212.67 gigapascal. We use the same formula for assessment 2. The second moment of inertia we get 0.45 multiplied by 10 power of negative 9, and Young modulus we get E equal to 144.68 gigapascal. Same for the next specimen. Moment of inertia we get 1.066 multiplied by 10 equal power of negative 9, and Young modulus we get 135.71 gigapascal. Next, compare the modulus of elasticity obtained with the theoretical value. So the formula is error equal to theoretical value minus experimental value divided by theoretical value multiplied by 100%. The first specimen, theoretical value is 210 gigapascal and experimental 212.67 gigapascal. You get 1.27%. Specimen 2, theoretical value is 210 gigapascal and experimental value is 144.68 gigapascal. We get 31.10%. And for the last assessment, we get theoretical value is 10201 gigapascal and experimental is 135.71 gigapascal. We get 35.38%. So that's all for the calculation.
Hi, my name is Anastasia. So today I will do the discussion part of this experiment. So in this discussion, we will derive about 3 graphs that we obtained from the experiment. So the first graph that we obtained is deflection versus loading. From this graph, we may deduce that the deflection is directly proportional with load. As the load is increased, the deflection also increased. The maximum point of deflection was at 1.15 mm, which is at 20 Newton, while the lowest point is at 0.28 mm at 5 Newton. So for the next graph, for the deflection versus span length, we also deduce that the graph is directly proportional, which is deflection is directly proportional with span length. As the span length increases, deflection also increase. So from this graph, the largest deflection we obtain is 0.52 mm at 600 mm of span length, while the lowest deflection is at 0.07 mm at 300 mm of span length. So next graph is deflection versus test of specimen height. So for this graph is a bit different from the two previous graphs. So for this graph, the deflection does not directly proportional with test specimen height. This is because the deflection of the beam reduced as the height of the specimen increased. The highest measured value of the deflection is at 0.46 mm at 4 mm of specimen height, while the lowest is at 0.08 mm at 8 mm of height. So there are some errors may occur throughout the experiment affecting the result. When alternating the span length, for example, parallax accuracy may arise. Setting the span length scale perpendicular with your eyes is one of the approaches to avoid this issue. Aside from parallax error, the readings at the gauge change before taking a reading, potentially preventing reliable data from being obtained. To avoid this error from occurring again, we must ensure that the specimen is free from external disturbance and wait for the time before taking the readings to ensure that the value remains at 0. So now I will explain about the importance to have several types of beam, such as C-beam, C-channel angle beam, and I-beam and hollow section beam. So the importance of having more than few beams is that we can employ them depending on the load application, structural phenomena that affect the members, and characteristics that regulate a member's structural capacity. So for point loads, uniformly and direct bending, moment or direct bending, and rotation are the most common types of load applications seen in engineering construction. So we can employ one or more structural phenomena like compression, shear, torsion, tension, and flexure depending on the type of load application. Resistance that may arise will also be detected in order to make the process of selecting the correct way of sectioning go as smooth as possible. So for example, the C-channel section resembles the letter C, is extensively used for load distribution with a minimal moment. C-channels are commonly employed as secondary structural elements, such as for joint supporting and the floor supporting member for ceiling assembly, since when used a multiple member system, they may provide the highest structural capacity. Thank you.
Conclusion. As our conclusion, our team was successful in obtaining and determining the link between load and deflection, span length and deflection, and height and deflection. As more weight is added to the beam, the deflection rises. As the span length grows, the deflection grows as well. The specimen's weight and height were maintained at the same levels. Along with the specimen height, the deflection likewise increases linearly. We also know that we can get the opposite type of data by changing the variables. The Young modulus was calculated using the data collected during the experiment. There were a few errors that could not be prevented throughout the experiment. Therefore, we took many safeguards to minimize them. During the experiments, for example, gauge readings fluctuated. As a result, we ensured that there are no extraneous forces operating on the hanger in order to increase precision. Setting our gaze perpendicular to the measurements reading also helped us prevent parallax errors.